Colligative properties are properties that depend on the concentration of a substance. So the property changes depending on how much solute is dissolved in the solvent. So in this diagram, the properties are going to change as we keep adding more moles of the substance into the solvent. Okay, so what are the colligative properties that we will be looking at? We'll be looking at vapor pressure, freezing point, boiling point, and osmotic pressure. And it's also important to note that there is a difference depending on whether the particles that are being dissolved as the solute are ionic or non-electrolytes. So let's take a look at what that means. The Vant-Hoff factor relates how many particles are dissolved, and it changes the overall effect of the colligative property. So here are two containers, and one container holds an ionic substance, potassium phosphate, and the other substance is sugar, C6H12O6, glucose. So when we put the potassium phosphate into a solvent, what happens is it dissociates. So that means that it breaks apart, and it breaks apart into 3 potassium ions and a 1 phosphate ion. When we put the sugar into a solvent, because it is not an electrolyte, it just stays as one particle. It stays as one sugar. So if I'm looking at the Vant-Hoff factor, for my potassium phosphate, 1 potassium phosphate yields me 4 ions, or 4 particles. It's a Vant-Hoff factor of 4. 1 glucose yields me 1 particle of glucose. So it only has a Vant-Hoff factor of 1. And this becomes very important when we start looking at the different equations that we have for the colligative properties. So let's see how this relates to our individual colligative properties. So the first specific colligative property we're going to look at is vapor pressure lowering. And what we see in the diagram here is we have non-volatile solutes. Non-volatile just means that they're not going to be gases at room temperature. And so by adding these non-volatile solutes to our solution, they lower our vapor pressure, which means that they're not going to evaporate. Okay, what does this mean? Well, our equation for vapor pressure lowering is Pi equals Xi times P naught. Okay, so let's look at what each of these factors represents. Pi is going to be your vapor pressure. Okay, so that's going to be where you end up with, what the vapor pressure lowering is. Xi is your mole fraction, which you will have to calculate. Pi naught, okay, or P naught is the pure vapor pressure. That is what the pure substance would have as a vapor pressure before you added the solute to it, okay? The reason that they all have this little sub-I is because it's telling us that these values have to be for the same substance. So for example, if we were looking at what is the lowered vapor pressure of water when I add salt to it, I would need to look up the pure vapor pressure of water, and I would need to find the mole fraction of water in my solution, and that would give me the vapor pressure lowering for the water. The next colligative property is freezing point depression. And in this graphic, you see that friends keep you from freezing. So we have these solutes that are going to insulate this particle, and they lower the freezing point, which means it has to be a lower temperature in order for the freezing to occur. The equation for freezing point depression is delta T equals K sub F, which is a constant, times molality times your Vant-Hoff factor. Okay, so let's take a closer look at this. Our delta T is going to be T final minus T initial. Okay, so we're looking for that change in temperature. Again, K sub F is going to be a constant value that you're going to look up at a constant chart. The molality is going to be your moles per kilogram, and then your I is your Vant-Hoff factor. So for example, if you were doing this for a substance such as NaCl, because sodium chloride is ionic and it dissolves into 2 ions, a sodium ion and a chloride ion, that gives you 2 particles. So you would multiply your answer by a factor of 2. Freezing point depression explains why roads are salted in the wintertime, walkways in the wintertime, because by adding the salt, we're lowering the temperature at which that solution, the salt water, has to be to freeze. So we're not melting as much as we're lowering the temperature that is required for that substance to freeze. In these problems, you're often going to be asked to find the change in temperature or perhaps to find a new freezing point, because they're going to assume that you already know the initial freezing point, so that you're looking for either the final freezing point or the change in the temperature. Boiling point elevation is very similar to freezing point depression. Here we see in the diagram where the solutes are surrounding this particle, making it harder for it to boil, to reach its boiling point. So this is boiling point elevation. Our equation is delta T equals K sub B times molality times the Vant Hoff factor. Okay, so again, our delta T is going to be T final minus T initial. K sub B is going to be our constant value. The M is molality, and I is our Vant Hoff factor. Okay, so again, if we were dealing with a substance such as sodium chloride, the fact that this is ionic and it dissolves into a sodium ion and a chloride ion means that we're multiplying by a factor of 2 because we have 2 particles. Also, like freezing point depression, you may be asked to find the temperature change, or you may be asked to find your final temperature. So some people put salt in their pasta water, or when you're making pasta, you add salt to the water, and that is for flavoring, but what it's actually doing from a chemical standpoint is it's increasing the boiling point of the water, which means that water has to get to a higher temperature in order to boil. So that is boiling point elevation in a practical sense. Our final colligative property is osmotic pressure. Osmotic pressure deals with the passage of a particle or a substance through a membrane, and that's going to exert pressure on the membrane, so that's what we're measuring here. So for our equation for osmotic pressure, we have pi, which is osmotic pressure, is equal to I, that's our Vant Hoff factor, times M for molarity, times R, which is going to be 8.314, that's our gas law constant, times T, which is temperature in Kelvin. So for osmotic pressure, we're going to be using our typical pressure units. Okay, so it could be atmospheres, kilopascals, anything like that. Because our R value is 8.314, we do want to make sure that we have a pressure in kilopascals when we use this equation, okay? But if they give you pressure in atmospheres or torr or something else, we can do a pressure conversion and convert it to kilopascals, and then we can use that information to solve for molarity or temperature or whatever we need to. So again, pi is our osmotic pressure, I is the Vant Hoff factor times molarity times 8.314 times our temperature in Kelvin.